I'm Antonio Sala, and in this video we are going to carry out an example of linearization of a function of two input variables using Matlab's symbolic math toolbox. We'll do a basic theory review, we'll compute the linearized model, and we'll superimpose the plots of the original function and that of the linearized model. Let us first discuss the function we are going to linearize in this example. I will define three symbolic variables to be used in my algebraic manipulations, and with this line I will define this function to linearize. I just invented it, it's nothing special. Matlab symbolic toolbox shows it in pretty form here. The operating point we are going to choose to linearize around it will be this one, x1.85, x2.5, and again it's just arbitrarily chosen, it's not any equilibrium point or whatever. That's usually the case in linearization of physical models. In here it's just two numbers. So in order to get the value of the function at that operating point, I will evaluate this f at this point with the symbolic toolbox, and that will render a symbolic expression. Here we have it, replacing x1 and x2 by these values, but okay, even if the symbolic toolbox cleverly stores symbolic expressions to avoid floating point round-off errors, I just want numbers to see in my example, so I will tell Matlab to evaluate those expressions to a number and show me such a number. So the function takes the value 0.92 in this operating point. So this 0.92 is what I would have obtained by evaluating this, with a hand calculator. So good, we have then the x and y coordinates of the operating point. So let's see a plot of the function before linearizing. I will plot a range of plus minus 2.1 in the first variable and plus minus 1.6 in the second variable around the operating point, and the function will be plot with the fsurf command. Also, this plot 3 will draw a ball at the chosen operating point. Here I have the three coordinates, three numbers. So let's see the result. Here we have it. It's, a function of two variables. I can open it in a figure window and move it a little bit, but okay. The goal will be computing, let's say, the tangent plane here, which is the operating point. So the function sort of resembles a parabola around here, but okay, we have some cosine deformation, whatever. So how do we compute the linearized model? Let's have a look at the theory, and then later on we'll discuss actual computations with Matlab code. The main idea of linearized models is based on the Taylor series around the chosen operating point, x up. So if I define this delta x as the increment of x, we can express a function, provided it is smooth and the required derivatives exist, with this expression. That says that the value of the function at another x point different to the operating point is the value at the operating point plus some stuff given by the sum of the first derivatives at the operating point times the increment of each of the coordinates, 1 and 2, plus 1 over 2 factorial, which is just 2 in this case, times the double sum of the second partial derivatives at the operating point times the products of increments, all the four combinations, plus 1 over 3 factorial the sum of the third partial derivatives at the operating point times the degree 3 products of increments plus fourth derivatives plus whatever. Nevertheless, these quadratic, cubic, etc. approximations are dismissed in the linearized model. So this fragment of the expression will be the linearized approximation, taking only the constant plus linear terms. But well, this is actually a fine expression because we have some constants, and the actual linear model requires a change of variable to increments also in f, in the sense that if I move to the left-hand side the value of f at the operating point, then f of x minus f at the operating point, I can name it increment of f. So the increment of f, well, will be approximately equal to the derivative with respect to x1 times increment of x1 plus derivative with respect to x2 times increment of x2. So this is the linearized model. However, as the usage of this linearized model, and in some cases the quadratic term also, is very frequent, these two terms are usually written in matrix expressions, in the sense that this term, I may define this row vector of partial derivatives and multiply it by this column vector of increments of each of the coordinates. Of course, I needed to evaluate them at the operating point, but well, this is a 1 times 2 row vector. This is a 2 times 1 column vector, so I get a 1 by 1 scalar because f is a number. Everything agrees, and this is a convenient way of representing this first summation. And then this left stuff is named Jacobian matrix, that I will, abusing the notation, denote it as df/dx, or well, we may also use, capital J if you wish. This df/dx is sort of informal stuff because, okay, we cannot take derivatives with respect to a vector, but okay, this matrix of partial derivatives called Jacobian times the increment in vector form gives me the incremental linearized model, or well, if I put the operating point at the other side, I will get a fine, let's say, adding a constant, linearized approximation. In fact, this quadratic term is also expressed in matrix form as follows. This is 2 times 1, this is 1 times 2, and this is also an abuse of notation denoting a matrix called Hessian, whose element ij is the relevant second derivative. And so in some cases we'll use it when analyzing the linearization error later on in a sequel video. Well, in some cases then this Hessian is used, but okay, the linearized model basically consists on forgetting about all this stuff and keeping this stuff, or in incremental notation, just keeping this. Good, so this reviews the basic theory. Let us now apply it with a symbolic toolbox to our particular example. So I will need to compute the Jacobian. I will not need to compute the Hessian, but okay, the Jacobian will be computed with the surprise Jacobian command of the symbolic toolbox. This is it. Jacobian of f gives me a 1 times 2 matrix with a partial derivative with respect to x1 and a partial derivative with respect to x2. As this is f, well, the derivatives with respect to x1, let's say, well, this will be x1. These other things will render 0 in the derivatives with respect to x1. And well, this thing will be minus sinus times 1.1. And well, you can pause and check that indeed Matlab knows how to compute derivatives. In fact, we can double check even with Matlab that the Jacobian is what it should be, just checking that indeed the partial derivative with respect to x1 is this thing, and the partial derivative with respect to x2 is that thing. Because, well, if I tell Matlab to explicitly compute such derivatives, then I can check that Jacobian does the work right. So good, then we have the Jacobian. So the linearized model will be just this thing. Here we have it repeated, and well, for later operations I will think on increment of f being the exact increment of the nonlinear stuff, and I will call the approximation increment of y equal to this Jacobian times increments. So if I were in a pen and paper examination, my linearized model would be evaluating the Jacobian, this expression there, at the operating point, and of course, as this will be, replacing in x1 and x2 some numbers, but Matlab will keep the symbolic expressions. I don't want them, so I will evaluate that stuff to a number because I wish Matlab to be a calculator. Then I will have these numerical values of the Jacobian, so my linearized model will be increment of y equal to this matrix times increment x1, increment x2, or, well, it's the same than saying that increment of y is this thing times increment of x1 plus 1.6 times increment of x2. Two ways of writing the same, of course. So this would finish my pen and paper examination about linearization, but okay, as we have Matlab, we can plot the linearized approximation and superimpose it to the original function to see how they fit. Of course, then the plot of the linearized approximation must be in absolute coordinates, not in incremental ones, because the original function plot we saw was in absolute ones. So we need a little bit of bookkeeping with Matlab code, in which, well, I have my symbolic x vector. This is my linearized approximation, the increment of y equal first element of Jacobian at the operating point times increment of x1 plus the second element of the Jacobian at the operating point times increment of x2. So I wrote that with a symbolic toolbox, but okay, as x is in absolute units in here and here, all three letters x1, x2, y are in absolute units. And then I tell Matlab to express this stuff with variable precision arithmetic for significant figures and put it in pretty form, and returns me this equation, which is the equation of a plane, which of course is the tangent plane to the function at the operating point. Of course, this expression in here can be readily encoded in an equivalent but more compact form using, of course, the full Jacobian matrix capital J and the column vector increment. But okay, this is just a compact form in matrix notation of writing the above. And of course, we get exactly the same expression. This is an implicit expression. In order to plot y, well, we just need to put this to the other side and plot that function y, which is the approximation. Solving for y is done in this line by the symbolic toolbox, giving me the highlighted expression, and then if I plot this function and the original one, They are both in absolute units, not incremental ones. Then I have here the f surf of the original function. I have here f surf of the linearized approximation. This is again a ball at the operating point. And here we have the function in color and the tangent plane linearized approximation in gray. So we can play with it a little bit to check that indeed we have the tangent plane at the operating point by looking from whatever side we wish. So in here we can have an intuition on what the linearized approximation is in this particular example. So we'll finish the video here. In this video we have shown a particular nonlinear function, we have reviewed the theory on the Taylor series, Jacobian, Hessian and whatever, and we have computed the linearized model, tangent plane in absolute coordinates, and in incremental coordinates just Jacobian matrix times increment of x. Of course, there is an approximation error depending on the curvature, let's say, of the function at the point of tangency between the approximations, which we'll discuss a little bit in a forthcoming video. For the moment being, we stop here. Thanks for watching.